I used to picture it as a type of a highway. And so on that one, you can put, the user can put any kind of trucks, limousines, little bicycles, whatever it's appropriate. That will be a normal type of road. However, I3C, it's an intelligent highway. It's got speed controls, it's got entry and exit signs, and all of those makes it more than just a straightforward type of transport system. Today I'm trying to speak about those points there, and after a short list of what, for the time being, I think are one of the good features of I3C, we're going to focus a little bit of the nuance, the timing controls, and some elements of flow control on this transport. This is a general picture of what the I3C highway looks like. It has various devices on that one. It's got masters from I3C. It's got a combination of main master and secondary master. It's got slaves. They are I3C slaves, and at the same time, it can actually converse back with legacy I2C devices. So there are, one of the good part of I3C is that it supports these several communication formats, all of those based on those basic two wires, and at the same time, it's got various type of protocols. The advantage of I3C is that it's an encapsulated type of arrangement where the bus management is done on the basic two wires. And after that one, during the real data transfer, it can use a number of protocols. One being the single data rate, the normal one, almost normal, almost similar to I2C. Then we have the high data rate systems where you have the double data rate, the DDR, and we have the symbols, the ternary symbols, where the two wires are actually used to transfer the data in a differential arrangement system, using both of those to transfer actually information, not like on the previous two where the S clock is just a supporting line. Now, those bus management features that makes the interface intelligent are listed on your screens. So one is the dynamic address assignment, which makes possible to set a priority rank for the devices on the bus. That priority rank is used for assigning the priority service for the in-band interrupt. Having this in-band interrupt capability gives the possibility for the device to get rid of the normal data ready interrupt or any other type of interrupt systems out of band. So it saves a lot of pins. The bus is an open bus. It can have the hot join devices that will come on the bus and they can ask permission to join, and they will. For the in-band interrupt, I just said, it's a procedure where any member of this I3C bus instantiation is got the possibility to request to transfer some information in direction of another one. We know that many devices, they have this hard pin reset. It's a physical pin. That function is actually replaced by the in-band hard reset. We have a procedure which is developed so that pin reset, it's actually not needed any longer. The philosophy behind of this development of I3C is that we would introduce as bus management features, global features that are essentially global, and they are helping various important applications. One of those ones is this timing control. So, which is used either for synchronizing the bus clients or to transfer a timestamp for asynchronous events. Now, for many type of interfaces, there are those agreements between the devices that participate with those ones. Well, I3C has got a supplementary layer, a higher layer of agreements, so to say. They are called common command codes. You're going to hear me eventually and my colleagues after that saying CCC. Those command codes are, as the word says, understood by all devices. They are divided in two categories. One, they are mandatory, and some other ones, they are optional. And they get implemented on any time that device is such, it's actually used. Certainly, you have the error detection on the system and the recovery. And one of the latest additions was the flow control. We had these requirements for various users of the I3C bus that how somebody can actually intervene and stop or ask for stopping that transaction. And those are elements of flow control that I'm going to speak about a little later. On the timing, I'm going to go now back, I mean straight to the two focus points that we have. So the timing control. I shouldn't say much about the importance of this. To me, it's kind of obvious. And there are two versions of this. One is to control the synchronous systems and events, meaning that there are applications, more so in the sensors world, where the sensors are actually taking samples at various moments, and then they have to transfer those samples values to the host. Now, if they are not synchronized in some way, then the data transfer can take place at erratic moments, and consequently, they keep the bus occupied for more than it is really necessary. I will explain later how this one saves the problem. And then, for many events, they are actually on an asynchronous type of basis. The present implementation on other interfaces is using a sort of pin that changes states, and that one is that change of state is time-stamped inside of the host, and so that one is considered the timestamp of the event. Well, that one is actually corrupted by the several factors. Some of those ones being that the bus might be busy whenever I want to do that type of transfer, or the host might be busy. If the host has got a multi-thread type of arrangement, it does something which has more important than that particular interruption, you won't get timestamp properly. And so those things are the target for being solved by the timing control system. This is a diagram, a real-time diagram, that is supposed to show how the thing works in reality. So the top line there, it shows three different type of sensors with different moments when they actually take samples. As you can see, the red one, it's rather often. The green, it's somewhere in between. And the blue, it's rare. Now, if the host has to, which essentially is the system, has to actually take data or all of those, then it will end up being awakened at these erratic moments. Now, being like that, in between, the system normally goes in a sleep state. To go in a sleep state, it takes a ramp down, which takes energy. To come back to read, it's a ramp up, which takes energy. Now, if all of those, So if all those samples were actually synchronized, then the host can awake only at predetermined times and can read all the samples at various moments here, or it can be just the ones that are available there, or for the fast one, it can read only those ones. Like that, you can see straight away that the ramp up and the ramp down, it's way less than it would if the system is actually non-synchronized. All those synchronization systems are related to a agreement between the host and the population of slaves. So they have to define in between a hardware clearly identifiable event that they can timestamp. Now, on the I3C, one of those events, it's actually the start of the communication, the real start, whenever that SDA line goes down. Now, in a normal development or application, there are many of those. You don't synchronize the system every time. You synchronize it only at a certain duration of this. So the sensors, they have to timestamp each of those start points, and they keep one overwriting the other one in a shadow type of register. And then when the command to synchronize the whole period comes, they will actually use that particular value as a reference for doing that. In order to do this process, we are using a common command code, which is set x time, CCC, that's the name of it. Now, the devices, they have to be configured, first of all. So we have three configurations. One is the output data rate, which is clear. It's, you set up your target device to present so many samples within such a long or short period of time. Then the TPH name comes from the T, which is the period, and PH, which is the phase. The reason being that it's not sufficient to actually synchronize the frequency, which will be the period. It's important to synchronize the start of that period, which will be the phase. So that's the TPH. And the innovative part of this control is that it gets rid of that inaccuracy related to when the real moment was perceived by the two devices. That is achieved by, first of all, there is one first command, which is the ST, meaning sync tick, which actually marks that last timestamp which was taken by the sensor is the one that's the reference. And then comes the delay time. The delay time is another information which informs the target how far back or how far after that moment was. So now it doesn't matter if you were with that sync tick at some precise moment, because you know how far back that precise moment was. You transfer that to the slave, and the slave will adjust its start of the TPH period. Consequently, it will adjust the frequency and the phase. Yeah, well, on the asynchronous system events, we have a couple of versions, depending on how important or how precise we need to have the timestamping. The basic one is the asynchronous mode 0. That one, it's essentially a ratio calculation between a scaling factor and the initial number. And the other ones, if the distance in time between the real event until it was really able to transfer that to the master, it's long. In that situation, there are available other enhanced modes of asynchronous, which are the first one, the asynchronous mode 1 is a development of the mode 0. The 2 and 3 are more sophisticated for more demanding type of applications. How basically does it work? So first of all, there is to be again, a mutual understanding between some hardware events. Those two hardware events are the ones that are considered like poles for this arrangement of the scaling. So on the second line here, you can see that, so the sensor has got one event. When it's got that event, it starts actually a counter. It's just a counter inside of it, and goes and tries to get the attention of the host. Once that attention of the host is at this hardware event, general hardware event, then the sensor will capture that first number, SC1, sensor counter 1. Because it's a mutual understanding between those two, the master will capture at this time as well its own timestamp on that one. And then it comes a procedure further than that. They start counting both in their internal timer counters. They don't need to know which one has got what. They just count in their own field. And once the second hardware event was actually achieved, then the slave transfers the SC1 and SC2 to the master, and master knows his reference point and does that calculation which is on the screen there. So like that, it's got exactly it actually infers back when the timestamp was in the master time domain, not in the slave. It doesn't need to know if the slave was running on 1 megahertz, 10 megahertz, 100 megahertz, whatever. It knows actually how many was back, how much was back in his own terms. The practical application here on SDR, the events are actually the first rising clock age after the in-band interrupt has been accepted. See, that's the thing. So it's going to be accepted. Then this is the first identifiable hardware event. And then comes the read of the mandatory data byte. And after the T bit, the immediately following rising S clock age is the second event. Now, it is possible that the first part, getting to the first hardware event, it takes long. And the master might know that he was busy doing something else, or it was actually necking, not acknowledging the request or blocking the request of the slave. So consequently, if it does like that, it is possible that this number is going to be too small, and consequently, the quantization error is going to be large. The master has the capability to do in that situation either to stall the clock or to change the speed of the transaction. So like that, it increases the number, the digital number that it is used as a reference for the calculating back the whole system. I think in broad lines that was it on the timing control. Elements of flow control. The flow control is very important. I'm wasting my time saying that because you know this. The challenge that we have in I3C is that being a high-speed bus, the devices are actually driving actively their data lane. So consequently, the receiver, which might want to interrupt the transaction, has no possibility to do it in a normal way because it will actually conflict, obviously, with the active drive. So because of that, we devised some procedures to allow that window of opportunity. One can call that one a breakpoint, if you would, where the receiver side can actually request or even stop. If it was the master could even stop the whole transaction. Those two apply to the DDR and to the ternary systems. Both of them, the DDR has got the SDA driven actively by the sender, whereas the ternary has got both lines driven actively. I put on the screen there those conditions. In DDR, we have the preamble, and the preamble allows some follow-up actions. That's the reason of the preambles. And within DDR, there are two specific moments. One is whenever the slave agrees to actually be read, and the other one is after the read procedure comes, whether or not the slave would agree to stop the transaction and leave the control to the master. The reason I'm saying that is that the preamble in that situation it's got two situations. So here, after the read command here, this one says it's accepted because it is a active and willing acceptance. And if the slave doesn't do anything, in other words, the preamble is high, it could be that either the slave does not want to transfer or the slave is not there. So that's why you have this combination. However, when you are on the read data, it goes exactly opposite. And in the little time that I still have, let's look at this one very quickly. So in the specs, you're going to see this type of signal diagrams. The bottom part here is the bottom, the extreme parts are whatever it is on the lines. So here is the S clock line. Here is the SDA line. They are the resultant of the action of the simultaneous action of the devices. Now, on the bottom, because it's close to the S clock, you're going to see the master, what the master does, and what the slave does. They are marked M underscore SCL, and the other one is S underscore SCL. On the top one, you have, similarly, on the SDA, and you have the same, the master here and the slave on top. There is a code on those lines. Wherever the line is continuous, you will have an active driven. So if you look at this, as an example, if you look here, this is the SDA on the slave. On this position, the slave drives actively. And the same, the master drives actively on the other side. The slave has only two possibilities, either drives or it is in high Z position. That one is depicted with dash to dots type of line. The master has got two actually other version, which is one, it is just high Z, which will be a continuous long line, or it is when it enables the pull-up, the pull-up class structure. Here, it's a show of how this thing works when the slave wants or doesn't want to continue the DDR. On your left-hand side, you have whenever the slave wants to go, and as you can see that on that one, the preamble 1 and preamble 0 are 1, 0. Consequently, because what? Because there, the slave are actually pulling down the SDA line. So consequently, it was signaling that it is a 0. If the slave is not there, here, or he doesn't want to do anything, then the master is going to read the 1, 1. So consequently, we know that there is no transfer further than that, and it will stop the read arrangement. As opposed to that, here, there is exactly the opposite situation. If the slave wants to actually continue the read arrangement, it will keep the two preamble bits 1, 1. That's to to preserve that speed, to do not change anything, it just doesn't do anything. It just stays there, saying that, okay, let's go ahead. Now, if it wants to stop it, then it will actually pull down the line. Consequently, those two are going to be 1, 0. Now, I won't go into detail because I'm running out of time. Sorry for that. This ending on DDR can actually take place in two versions. One, when you have ending with no CRC. In other words, if the ending of a transaction comes, then you go straight away for repeated start or for HDR exit symbol. Or it can be with CRC, like here, when after you are informed that you have to stop transaction, you still transfer the CRC, whichever the CRC is. For the time being, that CRC, it is the CRC5, and it's got a token. That token is fixed. It's C. It's a hex C. So that's what you see there. It's 1, 1, 0, 0. So, and this one applies to the whole system further down. And I would please apologize first, and then maybe you can look yourselves, please, on those things when they are the same in the specs, I mean in the version 1.1. On the ternary, we are in a different situation. That ternary system does not have any kind of preamble. So we introduced a possibility of configuring this ternary transaction, giving a window of opportunity after multiples of 16 ternary words, and which can be, again, configured. You can have this opportunity after every 16 words, or you can have a multiple of 16 words. What that opportunity is that whoever is transmitting, it's actually pull up two supplementary clocks, just 2 clocks, and in those clocks you have the same convention as you have so far, meaning that it is, if it is 1, 1, you go ahead. If it is 1, 0, then you stop. And this is the situation when the master does it, and the master is in control here because you can see it's continuous line. It controls the transfer. Or, in this situation, when the slave, it was exactly opposite. Anyway, those two are actually driven further by the whoever was continually transferring the data. I'd like to draw your attention to this new way in which we are actually depicting the CCCs. The difference here is actually, the new difference is that this is the graphic, meaning that after you have a direct type of transfer of CCC, then you can repeat the transfer for each slave using the R or the W, meaning the read or the write bit, to inform the receiver, the slave in this case, what do you want from it. You either write to it the defining byte of the CCC, or you get back from it whatever was that defining byte that is active within that slave. So, which is a normal transfer, it doesn't change anything. It's exactly a global read-write. And another thing is just to show how a direct CCC ends, because these are the possibilities. Can exit with a stop, can exit with the IEEE reserved, and then after that can be a next CCC, or it can be a direct address, or it can be a stop. Well, thank you very much. Thank you.